Okay, now we're going to look at Chapter 20, C and D. This is where we really get into some actual calculus here. The derivative function is our start of calculus. And what it is it's a function that describes the rate of change, the slope, the gradient at a certain point for a function. So it's just it's another function that helps you find lots and lots of rates of change. So we in A and B, we looked at very specific points, like what's the instantaneous rate of change when x is 2? What's the instantaneous rate of change when x is 3? Specific individual points. The derivative function allows us to find the rate of change at any point. So we have a function now, and we can use that to plug in any point and generate lots and lots of rates of change without having to go through the individual work for each one. So the derivative, the gradient function, or the derivative for any value of x, the gradient function gives the instantaneous rate of change, or the slope of the tangent line, at that point. We have some different notation for derivative functions. So back a long time ago, I should have looked at the specific dates. There were two people that started developing calculus at the same time. So this was Leibniz and Newton. And so they started exploring calculus. Now, they lived in different areas of the world, and so they were maybe competitive with each other, but they have different notations. They had different ways of understanding things. And so whenever we're working with the derivative function, there's going to be two different ways that you might see this. So the first way is if we're given an equation, y in terms of x. So y in terms of x. This is like the very start of graphing lines. You might have been given something like y equals 2x plus 5. You started graphing lines. This is y in terms of x. X's and y's. Then came along function notation. So if you're given it in function notation, this would be f of x equals 2x plus 5. These really mean the same thing. They're just different notations, and so our derivative function also carries different notations. So Leibniz developed the notation of dy by dx. You'll hear me say dy over dx or dy per dx. So it's just dy on top, dx on the bottom. It's the difference in y divided by the difference in x. This is like slope. Subtract the y's, subtract the x's, difference in y over difference in x. You'll hear dy by dx or just dy dx. And this is the notation for the derivative function if you're given y equals. If we're given a function f of x, then we represent the derivative function using just f prime of x with this little apostrophe. So if you're given this type of function, your derivative would be represented this way. This type of function, your derivative would be represented this way. So we have this little shortcut that works with our derivative functions. In class, I can show you why this works. It's kind of hard to do on a video. So on the video, we're just going to look at what it is. And it's a pretty easy just rule to follow. And what's super nice about this rule in this course is that on your IB reference sheet, it's given to you. So this right here is what I have written here. So you don't have to worry about memorizing. You just need to be able to apply. So what this says is if you have a function f of x, and it's a times x to a power, then the derivative will be this. So you take the n, notice we have an n here in our exponent, we drop it to the front, it appears there, and then you decrease your exponent by 1. So it started out as n, it decreases by 1. So it goes down 1 in your exponent, and the n gets multiplied to the front. This is the other notation. So if you're given an equation y equals a times x to the n, just with y instead of f of x, then we would say dy dx is equal to the same thing. It's just the other notation. So it says find the gradient function or derivative for this equation. So y equals x to the 8th. So since it's in y equals form, my derivative will be dy over dx. We're going to follow the rule. So we take the exponent, drop it to the front. There's nothing to multiply it by. There'd be a 1 there. 8 times 1 is 8. So it's 8x. We decrease our exponent by 1. So instead of an 8, it is a 7. And that's our derivative function. Okay. For b, there's a number in front this time. And we're also in f of x notation. When you're in f of x notation, your derivative is f prime of x, like this, with a little prime symbol. Same thing goes. We've got 5x to the third. You take the 3, drop it to the front, multiply it with the 5. 5 times 3 is 15. So drop the 3 to the front, multiply it with the 5, and your exponent decreases by 1. Question C is a little bit different. In order to understand this, we're going to have to rearrange it a little bit. So back in Algebra 1, you had exponent properties, and one of our exponent properties, so if you need a little reminder, if you have something to a negative power, in order to make that power positive, you flip it over. So vice versa, if you have something on the bottom and you want to move it to the top, then you can just change your exponent from a positive 3 to a negative 3. So our function will become y equals, it was x cubed in the bottom. I would like it to be on the top because this doesn't have a fraction in it. This rule doesn't. So I can write this as x to the negative 3 power. Now it looks like this form. It doesn't have the a component, but it does have an x to a power. So we're going to follow, since it's in y notation, it's dy dx. We take our exponent, we toss it to the front. So negative 3 goes in the front, x, and our power decreases by 1. So negative 3, if you subtract 1, you get negative 4. You could leave your derivative function like this. Alternatively, you could rewrite it with a positive power and leave the negative 3 on top. This is to a negative power. So x to the 4th would move to the bottom. This is probably a better way to write it, but the other way is also correct. It's just maybe not as good. They take it on the IB exam. So, okay. Consider the problems from 20AB notes. Find the instantaneous rate of change at the point x equals 3 for this equation. So this is the very last example on your previous notes from 20AB. I want to solve this problem by finding the derivative. So I want to, these are functions that describe the rate of change at that moment. I want to see if I can find that function and then use it to find the instantaneous rate of change at that moment. Let me go back here just for a second, this A. If we do what we did last time, and we type in our function, so in my y equals, I'll type in x to the 8th, and graph it. It's going to be super steep. There it is. Okay. Let's say I wanted to know what the slope is when x is 1. Okay. Well, last time we would type in our function. I want to know the instantaneous rate of change when x is 1. Second, calculate. Number 6, which is dy dx. Type 1, enter, and it says the instantaneous rate of change is 8.0000. That is 8. Okay? Well, let me plug in 1 here. 8 times 1 to the 7th gives us the same thing. So if we let's try a different point. So why don't we see what's the slope at negative 3. Let's see if that'll even show up. Oh, wow, that's big. Okay. So negative 17496. Negative 17,496. All right. Let's try to plug in negative 3 here and see if we get the same thing. 8 times negative 3 to the 7th. And there it is. So this function is where you can plug in and get the slope at any point, and it does seem to check out. So if we consider this problem, last time we went to our y equals to solve this problem. We typed in negative 1/2 x squared plus 5. We kind of peeked at the graph a little bit, and then we went second, calculate dy dx, and we typed in the 0.3, enter, and it told us -3 was our slope. So let's do the same problem, but let's use our exponent, let's use our derivative property, or power property for finding the derivative. So I want to find the derivative, dy over dx. So I'm going to take my exponent, I'm going to drop it to the front and multiply it by whatever's there. So -1/2 times 2 is -1 x. My exponent drops by 1, so it was a 2. Now it drops to 1, so it's just an x. And then the +5 is a constant. Whenever you take the derivative of a constant, it goes away. So you could think about this, if you don't like the, oh, well, it just magically goes away. This is like x to the 0. So if I drop that exponent 0 to the front, 5 times 0 is 0. So you would end up with 0x to the -1, but 0 times anything is 0, so it just goes away. So we just get this. This piece goes away. That's our derivative function. So we wanted to know what the slope is when x is 3. At that point, our derivative, dy dx, -1 times 3, is -3, if you plug it in. So this is the slope of the tangent line, or instantaneous rate of change at that point. So we have some other rules for derivatives. So they're kind of the same. We're just putting them all together. If you have a constant, this thing happens here, where you drop the 0 and multiply it by 0, and it goes away. So the derivative of a constant, a, is just going to be 0, nothing. The derivative, if you have x to the n with no number in front, you just drop the n to the front and decrease the exponent by 1. Same thing if you have a number in front, an a, you just take the n times the a, drop the exponent by 1. If you have multiple functions added together, so multiple polynomial functions, then you can just take the derivative of u and the derivative of v and add them together. So we'll look at that on the back, but you just do the derivative of each and then add them together. Let's flip this paper over and try some others. Find f prime of x for each. This means find the derivative function. This is our derivative function. So I'm going to do f prime of x. I treat each of these individually. I'm going to find the derivative of each. So I take the 3, drop it to the front. 5 times 3 is 15. X. Exponent decreases by 1. Plus, this x is to the first power. We drop the 1 to the front. 2 times 1 is 2. Our x would be to the 0 power. But that is x, anything to the 0 power is 1. So this is just 15x squared plus 2. All right, question B. We've got these fractions again. We need to get it out of the fraction mode so that we can better understand it. So if you have something on the bottom and you need to move it to the top, you have to change the sign of the exponent. So if it's on top, you can move it to the bottom, bottom to the top. You just have to change the sign of the exponent. So I'm going to rewrite this function, f of x, leave the x alone, x minus 3, but I need to flip this up to the top, and I make the exponent negative to do that. Okay, that is an exponent property from Algebra 1, plus 4, flip that up to the top by making the exponent negative. So now we're here. And we can find the derivative function by doing our power property. So my first term is just x, so it's x to the first power. This would just become, the 1 would go to the front. The x would drop one exponent down to x to the 0. Do the same thing for the next one. We take the negative 1 exponent, we multiply it to the number in the front. So plus negative 3 times negative 1 is 3, x, and our exponent drops by 1. Negative 1 minus 1 is negative 2. The last one, we do the same thing. We take 4 times negative 5, that's negative 20, x, and our exponent drops by 1. Negative 5 minus 1 is negative 6. The best way to write, prime. The best way to write this answer, x to the 0, anything to the 0 is just 1. So 1 times 1 is 1, plus things that are to negative exponents flip to the bottom for the exponent to become positive. And same thing here, flips to the bottom. Okay, question C. I don't know where I came up with 5. When you have another issue, we've got an entire fraction. So I want to simplify this, I'm going to divide both parts by x so that it looks more like this question. So this will be, we'll have x cubed over x minus 4 over x. Divide both pieces of that. Oh, sorry. I'm losing my mind. We're just rewriting the function. Okay, we're just rewriting the function. This is not the derivative. And then we'll simplify this. So my function, x cubed divided by x, is x squared. One of those x's cancels. And we have to get this x up to the top. So this will be minus 4x to the negative 1 in order to flip it up to the top. Now we're ready to find the derivative because it looks like our power property, where we have x to a power, we have a number times x to a power. So we can do our derivative function. We drop the power to the front, decrease the exponent by 1. Drop the power to the front, decrease the exponent by 1. The best way to rewrite with a negative exponent is to flip it and make it positive. Ooh, that squeak is terrible. So there it is. That's our derivative function. On part D, we don't have a strategy right now for when we have them grouped into a power. So we are going to have to distribute this out. So to simplify my function, I'm going to do 2x minus 3 times 2x minus 3. It's 4x squared minus 6x minus 6x plus 9. So another way to write this by using the double distributive property is 4x squared minus 12x plus 9. And I'm going to find the derivative of this. Now it's in the correct form. Number times x to a power. Number times x to a power. And then just a number. So our derivative, I don't know why I keep doing that negative 1 thing. Probably because I'm teaching that in a different class. So we drop the power to the front. 4 times 2 is 8. Drop the power from 2 to 1. You might start noticing if it's just an x, that x ends up going away. So the 1 multiplies to the front. Negative 12 times 1 is negative 12. And then it would be x to the 0 would go away. We can ignore constants because they have a derivative of 0. So there's our function. Okay, let's actually solve a little problem with this. Find the gradient function of that. Gradient function is the same thing as the derivative. And find the gradient of the tangent to the function at the point where x is 2. I'm going to do this both derivative way and then check it using my calculator. So to find the derivative of this, we first have to rewrite it in the correct form. The x squared is fine, but we can't have a fraction. So I need to take the x and move it up to the top. So we'll have negative 4x. The x is to the first power in the bottom, so it's going to be to the negative 1. Now we're going to find the gradient function, or the derivative function for this. We drop our exponent to the front, 2x, it goes down by 1. The exponent to the front, negative 4 times negative 1 is positive 4x to the negative 2. Drop negative 1 minus 1 is negative 2. Once again, a better way to write this would be 2x, x to the 1 is just x, plus 4 over x squared. That's the first piece it asks, find the gradient function. Now I want to find the gradient of the tangent line at the point x equals 2. So I'm going to plug in 2. Two times 2 plus 4 over 2 squared. This is 4 plus 4 over 4. I get 5. So if I plug in 2 to my gradient function, that tells me the gradient of the tangent line is 5 at that point. Graphing calculator check. I'm going to type in this function, x squared minus 4. And you guys like the alpha y equals fancy fraction if you like. You can just do the original. You don't have to rewrite it over x like this. Okay, that's this original, very original function. If I graph it, see what it looks like on a 10 by 10 here. There it is. We want to know when x is 3. Looks like it's increasing, but let's see. Second, calculate. We're going to calculate the derivative. You can scroll, but it doesn't usually work. So I'm just, oh, sorry, we're looking at 2. I don't know where I came up with 3. So at 2, it looks like it's probably increasing there. So type 2, enter, and 5.00003. So that is 5, which is what we found here. Okay, so this is a good way to double check. On the IB exam, you will have to be able to produce this function, but you can get this value from your table. Okay, last question. The height of a tree in feet for a given year since being planted is given by this equation. So h equals 1/2 t squared plus 5. They want us to find dh dt. It's usually dy dx. It became h because our y is h, and t because our x is t. So dh dt is the same thing as dy dx. It's just our y is h and our x is t. So whenever I find dh dt, you can think difference in height over the difference in time. So we're going to take our power property here, take our exponent, drop it to the front. Half times 2 is 1, t to the first. Constants just go away. So that 5 just goes away because you'd end up multiplying it by 0, a t to the 0, and it disappears. So here's our derivative function. Interpret its meaning. Okay. So remember, this is the gradient function. This is a description of rate of change. So we're looking at the change in height over the change in time. So this function it gives the change in tree height over time. So if I were to maybe plug in 3 years, this is increasing. So if I plug in a 3, then it'd be 3 feet per year. So height is in feet, time is in years. So whatever this gives us is feet per year. So after 3 years, it is growing 3 feet per year. At 10 years, plug in 10, 1 times 10 is 10. 10 years, it's growing 10 feet per year. Okay? This is a description of what that means. All right, thanks for watching. This covers sections C and D. Once again, your homework assignments are listed on Canvas, so please take the time to start working on those.